Okay, let me talk briefly about the overview of option. And so let's just start. I have a video on Black-Scholes formulas, so I will make it quick. Basically the Black-Scholes formula give us a framework on pricing derivatives. So the basic assumption we're having is just a second order like a Taylor expansion with assumption of the stock price is going with a drift term and a volatility term, in the sense that it just goes exponentially over time, and then with a volatility, essentially kind of like a Brownian motion added to it. So yeah, this is Ito's, like from the Ito's calculus, and then we know the derivative is based on, say, stock price, strike price, drift, volatility, and then time to maturity. And then from here we assume no arbitrage, such the drift term become a risk-free interest rate, and with some calculation, which you can see, I will try to remember to put in the link. We have a call price and put price as for the stock option, and then where the D plus minus, sometimes it can be also called as like a D1 equals D plus, or D2 equals D minus. This is another convention. Just bring those chalk. So where the Y is dividend yield, R is risk-free rate, and tau is the time to maturity, and then the N here is the integration of standard normal distribution from negative infinity to x, and then the S is the stock price and K is the strike price. So mostly of this video, I will mostly talk about the Greeks. I'm just sourcing it from the Practical Guide to Quantitative Finance interviews, so that I can. It has a pretty good and concise understanding of the derivatives. Of the Greeks. They just gave a quick overview. Delta is a derivative of stock price, so sensitivity to the stock price is almost all similar things. It's how much change for the given stock price the option changes. And then same for gamma, which is change of delta with given stock price change. Theta is a time decay, so as the time goes, your stock is your options, how much it changed. Vega is a price due to a change due to volatility, and rho is sensitivity to interest rate. Let's just start from delta. Delta for call option is e to the negative y tau n d plus, and then put delta with e to the negative e to the y tau and negative d plus, I assume. Oh, sorry. It's oh yeah, of course. It's, keep in mind that d is a function of s and of x as well. So it'll be there we go. And So I think of all of those, it's important for us to have intuitive understanding of the behavior of all the Greeks. So let's just draw a plot. Of the delta of a call option versus strike price spot. Spot, and then so this is the stock price pretty much, and then this is the, let's just say this is the, probably good to just see this is S, so it's less confusion. S, this is S, and here is K, strike price. And we can plot out and let's say at a given for a given strike price here, as for different time to maturity, it will behave differently, as you would imagine. So let's just do a brain exercise. If you're closer to the maturity, you want to stop move. You want the stock once the stock goes much further from the strike price. The stock prices go furthest from strike price, then they're gonna expire out of the money, or deep in the money, in the sense that you wouldn't care either way. But it's really close. It's really close. Stock price is really close to the strike price. It will have relatively big slope in the sense that it really care about the change. So let's just say this is like tau equals 10 days, and it will look something like this. And as you can imagine, the longer it takes, it seems like there's more possibility in the future. So it's not really, the price of the option doesn't necessarily care nearly as much as the stock changes, because at that point, the volatility plays a more important role than it's playing more important role than the stock. At least that's what I would intuitively think. But correct me if I'm wrong. I'm not in the field yet. Hopefully soon. So you can imagine easily with like maturity day, say 1 month, 30 days, or 20 days. And then even further out, you would imagine this is like maybe like tau equals 60 days. And that's the same thing, similar things for put. As you can imagine, this whole formula, just flip it down. Oh. Guess I need to erase these. Right, so here's like a very brief of for the delta. And just to keep in mind, I probably, it's a good idea to say delta equals to df ds. Just making incredibly big. Because we have space. And then the next one is gamma. Let's say gamma is the change of delta over stock of change of stock price. So it looks like this. So the gamma for call or put equals you have, I guess it's probably easier to say this way, huh? Because there's so many things inside. E to the negative y l divided by s sigma square root l. And let's do the same exercise. Gamma stock price, and the strike price somewhere here. You can imagine this function to the derivative as what it looks like. It's quite intuitive. For the one that is closest to the expiration date, it will have the sharpest of all near the strike price. So because it's just a one more derivative, so it's like tau equals 10 days, and then similar things with I would imagine something like this. It's 20 days, which is 1 month. And then even flatter as the expiration date is further away. And there we go. That's gamma. I didn't think this through, isn't it? We need one more talk, or maybe I would confiscate this part for the rho, which is less important because rho is less sensitive. It's because interest rate doesn't change as much. Anyway, so theta is df dt, which is time decay. If you go to Wall Street Bet, people really need to know theta to just buy like all of money options in like a day, day of data maturity. Anyway, so it's theta, so the call option. Oh boy, that's kind of long. As negative as n d plus sigma e y 2 square root tau plus y as y tau minus d minus. There you go. And similarly, theta put, just almost similar, negative d plus sigma 1 tau 2 well, space. Okay, oh, so that's the difference. I guess that's the only difference. No. Similar exercise, plot it out, see what have some intuitive understanding of what happened. Call option. You can imagine as you really close to the expiration date, if it's really close, if it's in the money, you're just losing the time premium, but it has internal values. So on the right, strike price on the strike price. If the strike price is strike price is higher, stock price is higher than the strike price, like in this area, you will be close to, you will have easier time. But of course, the theta will be much bigger near the for the near expiration date, and for the little bit further away, it's less pricey, but it's still gonna hurt. So if you really have the money to buy these, to buy the, and you don't need to worry about like the time decay into your life, like when you're a little bit out of a little bit away from the expiration date, since it won't cost you like every minute. So here's theta, time decay. And now it's Vega. Vega call and put this S e to the negative y tau square root tau D1. There we go. Just to remind myself, V is the sensitivity to the volatility. Same thing, let's plot it out. Vega, call or put. Stock price, strike price. These are plotted out. I have to wing it, which I don't know if I could. Yeah, the stock price, the strike price. This is I will try to extend this video, and I need to plot this out.